This group chat, somebody put in the group chat, and it's just going off.
That is something wrong.
Yeah, another thing, get your phone usage out of your system. Get it put away. Stat. Again, same as all my classes. I don't want to see it. Oh yeah, I've seen it. Constant velocity, right? Yeah. And relative motion, right? That guy in the air has the same motion in the horizontal plane as the vehicle. That's why when he jumps in the air, he doesn't fall off the end. That's good. So you guys had some homework due. So two things. Two of them. One was the vector worksheet, right? That was practicing, like, how do you break a vector into components, right? That one should have been 4 just simple ones, kind of like what we did, the SOHCAHTOA, using trig, breaking up the components and write what component is the x, one component is the y. And then the second part was just a couple conceptual questions. So you should have read 4.1, 4.2. That was over the stuff we learned about, and it was just reviewing it from the textbook's perspective. And then the 4 conceptual questions were basically, after reading that, see if you understood like what I was talking about in the book, basically. Now, we talked about it in here. So that's what I need to get from you guys first. If you did your questions on the back of the vector worksheet, that's fine. I just need the vector worksheet and then the conceptual questions. If you did it on a scratch piece of paper, that's fine too. You guys have those to turn in? Huh?
There's a worksheet with a copy of questions.
Okay, that's fine. Again, I'll take what you have. Aiden? It's half credit up through the grading quarter.
You're just going 0.
No, I'm not that brutal. If you want to turn in something late to me, you can do it at any time through the grading quarter, which is October 7th.
Okay.
Now, ideally, you're going to shoot yourself in the foot if you're going to wait until October 6th to turn in this assignment, because by then we've already done the unit, taken the test, and moved on. So if you don't have it done, you can still turn in late for half credit. I just need that ideally as soon as possible so you can stay on track and actually get the benefit from homework, which is why I give it. But all grades will be, you could turn in late until October 7th. So I just need to collect those from you guys. I'll try to get those graded as soon as I can. I think I can get them done by next class. Thank you. Oh, this is what I needed. This is what I needed for our class, Brody.
What is that?
3. This is the measure. Remember we did measuring, Trevor? Part of that lesson was supposed to measure a hole with the dial calipers. Well, I didn't have the freaking parts, so they didn't send them. Now I have the parts. Because we were going to measure the paper clip, do that kind of quickly, and then let you guys measure the holes with the dial calipers, but lo and behold, they didn't send the parts. Well, at least I got them. Oh yeah, so homework, you got anything? You got anything from you guys?
One Aiden spoke.
Okay.
I emailed you because I didn't understand it.
Okay, and I was teaching all day and I just saw your email. Is there anything else from the back?
I realized that right when I got here, and I was like, hey,
Of the vector? Yes. I think I have spares. Oh, thank you. Do I have?
Overview. Yeah.
No.
But did you see the end of the green for those?
It's a common problem. Sorry, do you want to go for the have to respect? Sure. Just show us some gameplay. It's like, excuse me. I am Andre.
All right. So what I want to do is I want to give you guys a little like class challenge to try and figure out. I think I've done one before, but I can't remember. Here. Yep. Not this. So one, remember last class we finished let me zoom in a little more. Wait, I want this one first. So remember last time we talked about this thing called equilibrium. So I want to pose this as like a challenge question for you to think about. We'll review equilibrium. I want to see what you remember from last class when we talked about equilibrium and what that meant, how it applied to forces. So this question, there's a painter who has a weight of 600 newtons. His paint bucket weighs 100 newtons. He's on this painter scaffold, and it's attached at these two places. These are scales, like spring scales, that measure the force acting on those scales. This scale says that there's 700 newtons pulling on this scale and 500 newtons on that scale. The question that's being asked, if he's 600 newtons and the paint's 100 newtons, how much does this scaffold weigh? Right? The scaffold that he's standing on. The question is, how much does that scaffold weigh given this information? So feel free to, we got a guess of 500? Feel free to talk. I want us to solve this together. So shout out like stuff what you're thinking. First, like what would equilibrium mean?
It has to balance out. They have to equal each other.
Yeah.
So,
That's right. We talked about that equilibrium.
so we know 700 newtons so far with the hem and the paint bucket. It's 700 newtons.
So he's saying 600 for the guy, 100 for the paint.
That's 700, and 700 is on that side. And so if the other side is holding 500 newtons, that's the rest of it.
Okay, so Ethan's saying these weigh 700 newtons. Well, that's 700 newtons. Those would be balanced. But this one's supporting 500, so that the scaffold has to be 500. You like that answer? Does it make sense using the concept of equilibrium? So this weight, 600 newtons, that's a force. Weight is a force. Well, we know its magnitude. What direction is his weight pointed? Straight down, right? Gravity creates weight. Gravity's pulling things to the center of the earth. So gravity's pulling him with 600 newtons, pulling the paint bucket with 100 newtons. So that's 700 newtons down. These spring scales are supporting that weight. So this is reading 700 newtons of supporting weight, so going up, 500 going up. Let me draw this so that it's more clear. Earlier today in chem physics, we're doing nuclear chemistry, so we're looking at radiation. I had the legitimate Geiger counter counting the radiation. I had radioactive samples. Just for reference, one of them gave off 4,000 radiation particles in 30 seconds. So I was a little nervous holding that sample. But anyway, side note.
Did you get it?
No. Goodness no. So 600, 100, 500, 700. What we need is the scaffold. Well, can I use equilibrium and say, if this is balanced in equilibrium, the up and the down forces need to be balanced. So total, what's my up force? Well, 700 plus 500 is what? 1200. I know that has to be balanced. This is well, it has to equal 1200. Well, 600 plus 100 is 700. 700 plus what gives you 1200? 500. So this mystery, this unknown scaffold weight is 500. So here's like a full explanation. And they drew their picture a little better than mine, but right? 700 supporting up, 500 supporting up has to be equal to the 600 pulling down, the 100 pulling down, and then the scaffold's weight. Well, just make it an algebra equation. The ups have to equal the downs. You got one unknown, do algebra. All right? So that was touching back on that concept of equilibrium. The next one, I have one more. The next one, I want you to be explicitly mindful of Newton's first law. Does anybody remember what Newton's first law was? Yeah. Very simplified, but that's exactly right.
Yeah, sorry, I kind of forgot.
No, that's all right. As long as you get the concept, that's important. Ethan, I think I heard you mumbling it.
Yeah.
The second part is not only does an object in motion stay in motion, unless there's some force that acts on it to change its motion. And an object at rest, it stays there. Bingo. And when it's talking about motion, it's actually talking about acceleration. I could be moving the same speed, and my motion's not changing until I accelerate. If I'm sitting here, I have no motion, but it's also not changing until I apply that force. Think about that concept when you answer this question. So this one says you got a heavy ball on a string, and it's swinging. Well, you're going to pick it up and let it swing, and it's going to impact a razor blade that's going to sever the rope. Well, you got to predict what will happen to the ball when it hits that razor blade and cuts the string. What's that ball's motion going to continue to do? There's three options. The first one is as soon as it's swinging and as soon as it hits the razor blade, it's going to drop straight down. Second one, it'll keep going and then start to fall off. The third one, when it hits the string, it'll keep going up and level out. Hearing a lot of B. Any other thoughts? Why do we say B?
Because the ball's still in motion.
Right. In both of these, the ball's still in motion. What makes us select B?
Because so far the motion has been this way and down, and so when it drops, it's going to keep going in whichever direction it was last moving.
Okay. So Ethan's saying if you cut that cord, the motion is going to still try and do what it's always been doing. He was saying it was swinging down and to the right. Well, it's going to keep going that way. What would happen if I don't cut the cord? It swings, right? Isn't that because the string holds it there?
Yes.
The string is causing it to swing back and forth. If I sever that, I know it's not going to come back up, right? That doesn't make any sense. There's nothing acting on the ball after that cord is cut, except what? Gravity. Its motion is definitely going to change. because you have gravity acting on it. It's an outside force. This defies gravity. That's telling me my ball is floating with nothing acting on it.
Wouldn't, if you put the razor this way a little more, it would kind of go up because it started moving up?
It would. You're right. Because then you end up basically throwing it, and it keeps going up until gravity pulls it. This one makes no sense. Right? I just cut the cord. Well, what caused it to go straight down?
The razor absorbs all of the
Stops it dead. But that doesn't make sense because it should keep going. It wants to stay. It's moving in this direction. Well, if nothing opposes it, it's going to keep moving. So that's exactly right. When that ball is severed, all its motion is this way. Right? It's swinging, and I cut the cord. Well, it was moving exactly this way. It's going to keep doing that. But as soon as I cut the cord, gravity can act freely. Gravity is going to start pulling it down. Now it's in projectile motion. This is the same at any point in time. There's nothing acting in this direction to change its motion. It's just going to go that same speed forever until something stops it. In the y direction, gravity is acting on it. Gravity is changing its motion. So Newton's first law doesn't apply. It's not going to stay in that same motion because there is an outside force that's acting on it and it's changing its motion. It's accelerating it downward. That's just free fall, right? So some of these, I like these questions. They're very simple, but they're very conceptual. You have to understand the topic in order to see through the problem. Some of these are going to get really tricky. Some of these I get wrong when I look at them first, which is very humbling. Yes, and very reassuring. The next thing I want to do, I think I have queued up to finish. Oops, not that. This. Or start this, sorry. Now we're going to look at Newton's second law. All right? Let me throw off one more light so that it's easier to see. Newton's second law, does anybody know it off the top of their head? I don't expect you to.
With force, mass, acceleration, I'm just going to say force equals mass and acceleration.
You would be correct.
Did you just say that?
What?
Did you just say the whole second?
Yeah.
Did
He was saying,
I couldn't really hear you.
Mr. Heisman, try and get Evan real quick for newspaper. I
for
promise you it'll be real quick.
Like a minute.
like a minute? Yeah. Go ahead, Evan.
Hi, Maggie.
Yep.
Maggie, what's up?
Newton's second law, Ethan was right. He was saying, well, I see force, mass, acceleration. Sounds like F equals ma. He's exactly right. Newton's second law is literally this equation. That's all it is. So Newton's first law, object in motion, it's going to stay in motion unless some force changes it. Changes its direction, slows it down, speeds it up. It's going to stay still unless some force causes it to get going. Newton's second law, literally just this equation. Now this is written a little different. We always say F equals ma. But this is just algebraically rearranging it. Notice mass is the scalar. Makes sense. Mass is how much matter is in an object. Right? 10 kilograms. That doesn't have a direction. It wouldn't make sense for that to have a direction. That's a scalar. These two are vectors. Acceleration. What is our units for acceleration? Keep going. Meters per second squared, right? Acceleration is the rate of change of velocity. Am I speeding up a lot? So my velocity goes up a ton every second? Or does it accelerate really slowly? Meaning my velocity only goes up a little bit every second. So we got meters per second squared. What are the units of force? Those are 3 variables. What's force measured in? Remember, we want to think about not U.S., not the United States world, science world, physics world. Guys, remember the unit? He was a really famous scientist. Newton. Newton is how we measure force in science class. Mass we talked about was kilograms and then meters per second squared. The imperial units, aka the United States, how do we measure force? Close, that's pressure. Part of that, just pounds, right? I weigh 200 pounds. That's gravity's force on my mass. How do we measure mass? I don't think anyone knows this. I'll be a little impressed if someone knows how you measure mass in the United States or in imperial units. It's the weirdest term ever. Anybody? No, slugs.
Of course.
Yeah, of course. It's ridiculous.
How many slugs do you weigh?
Yeah, and
About them.
technically, I think I misspoke last class. I think I said this guy weighs 5 kilograms or something. Why is that me misspeaking?
Because his mass is 5.
Yes. And I apologize because that actually, it sounds trivial, but it's a big deal. It was not true of me to say he weighs 5 kilograms. Weight is a force. We're not measuring mass when we look at weight. Now, I weigh 200 pounds, but I would say I have a mass of, I don't know how many slugs I am, but. So try and catch me on that. If I ever say, let's weigh it, how many grams is it? Or if I say it weighs 10 kilograms, catch me and call me on that, all right? And then we do feet per second squared. We measure time in seconds still, but we measure our distances in feet. Sometimes they rearrange those. They do pound force, pound mass, instead of using slugs. So we had a 1 kilogram mass that we applied a small force on, and it had a small acceleration. Right? It picked up speed a little bit, it kept getting faster. What happens if we have the same mass, but we apply a big force? Big acceleration. Right? Its speed increased very quickly over time. It accelerated very quickly. Again, if you have a middle ground, you have a middle acceleration. And we'll call it, say, 1. Well, if my acceleration was 1 and my kilograms was 1, the force I applied was a Newton. Right? Remember Newton's second law, what we're doing, acceleration is force divided by mass. So if I have acceleration equals force, we didn't know the force. We knew the acceleration was 1 and the mass was 1. Well, shoot. 1 divided by 1 equals 1. 1. So my force is 1 Newton. Mind blown, huh? It's literally just this equation. How does this work? Do you see something weird about that equation? The math makes sense, doesn't it? 1 divided by 1 equals 1. Do the units match? No. This is meters per second squared. This is newtons per kilogram. Well, what the heck? This has to work. For this equation to be true, my units have to work. Otherwise, it doesn't make any sense. So how does it work? This is the definition of a Newton. A Newton equals 1 kilogram times meter per second squared. A Newton is these units combined into something we call a Newton, the force. That's the common unit we'll always use. But you need to remember that if you broke it into its smallest pieces, it actually is a kilogram meter per second squared. Well, let's try to figure that out. Or at least I want to show you the math. That was Newton's second law, right? Acceleration is the force over mass. It's the same thing as F equals ma, right? Just do my algebra. Ma equals F. That works. But we want to focus just on this equation. If I said acceleration we know is meters per second squared. Mass is in kilograms. What did we just say a Newton was equal to? A Newton, if we replace this, we know it's newtons, but newtons are actually a kilogram meter per second squared. Well, let's do our algebra. The easy way is just multiply across. Right? I want to take this quantity and multiply by the reciprocal to get rid of it on this side. Then I have to multiply this. Boom. So our units, they work, don't they? I wanted to prove to you guys, or to show you, that the units will work. Now we're going to use newtons for force. Totally valid. But you always have to remember a newton is actually a kilogram meter per second squared. Now you can always figure that out, right? If you forget this, you can always say like, oh, I know force is mass times acceleration. I know force is newtons, but I can't remember what the units are. Well, mass I know is kilogram. Acceleration I know is meter per second squared. You can always remind yourself, well, a newton equals a kilogram meter per second squared. So if you ever forget that, you can always just use the equation and have the units tell you. All right? How would we figure out the force of gravity acting on a 1 kilogram object? Can we do that? Yeah. Ethan just said our acceleration, we know. Gravity always acts with 9.8 meters per second squared. We know the mass, we can figure out the force. What we're solving for right now, 1 kilogram, 8 meters per second squared. Is the definition of a Newton. Oh. math on. So when we have a kilogram object, to get it to move by gravity's acceleration, you need 9.8 newtons. Well, yeah, you could break this down. If I change this to 1 meter per second squared, I get 1 newton. That matches how we define what a newton is. All right? Otherwise, just know F equals ma. A lot of times you can just plug and chug. I know 2 of them, just do my algebra. Make sure I know my units and let my units tell me the answer. Do you guys remember what this sigma, that symbol means? I know I shared it last class. Do you remember what that symbol means? Sigma means the sum of. So this means the sum of the forces. So it's not just a force. If we're looking at the acceleration of something, we want to know all the forces that are causing it to accelerate. If we add all those forces up, we could write it as F net. Net is, right, have you ever heard that? Like net income? That's what the resultant income is. That's the grand total at the end of the day. The net force is, after you figure out everything, what's the total force in that direction? So then you could write F equals ma. But it's always implied as a net force, the total force. The force of gravity on an object is defined as the weight. So you could say the weight of something is equal to its mass times gravity's acceleration. The force that you produce is what we call weight. Right? Anybody know how many kilograms are in a 45-pound plate in the gym?
20.4.
Did you read it or did you know?
No.
Did you read it here?
Yeah, it's right there.
Have you guys ever noticed this?
Yeah.
When you go to the gym, we do pounds. We're Americans. We are weird. We are weird.
The only one.
We are literally weird compared to the rest of the world.
We
The
are.
rest of the world does the metric
Except
system.
for
It makes so much more sense.
Except for 2 other countries. Liberia uses.
Did you look it up?
No.
I didn't know which other countries. I knew a couple.
Liberia's one. I don't know what the other one is.
Yeah, I don't know.
So like, not where you from? That is weird.
Yeah.
Good for them.
Like if you go to France and you ask someone how much they weigh, they're going to probably tell you in newtons.
Actually, they're probably gonna smack you because it's not weird.
And actually, technically, they'll probably give you kilograms. Even though scientifically that's wrong, that's how they view it.
And that's why they have El Royale or the Royale.
Remember? No, weight. If I ask someone how much you weigh and you tell me 100 kilograms,
Yeah.
that's a mass. That's completely irrelevant to weight. Because weight is a force.
Try and
So-
order a quarter pounder in
Yeah.
any other country.
In the U.S., we use pound as sometimes a volume and a weight. Right? You ever have cereal boxes? They use it sometimes as a volume. Like ounces. Ounces could be weight or a volume. So we got the units all screwed up. Anyway, we don't care about this. We want the mass of an object. We measure mass in kilograms. The mass of my object is 24 kilograms. I want to calculate the weight.
45.
Actually, no, because that would be in English units.
Shoot.
We got if this was slugs, we could calculate it in pounds. But we know that there's this much mass. What's gravity's acceleration on this object? Yeah. Again, from now on, we're going to use 9.8 because that's actually what it is. So if you do a homework problem and it asks you like to do this, you're going to use 9.8. 9.8 is gravity's acceleration. Now, if we do a quiz in class, at the top of the quiz, I'll specify you can't use your calculator. Use g equals 10 meters per second for simplicity. When I directly tell you, then you can cheat and use 10 for the sake of math. But I want you guys to be clear, moving forward, 9.8 will be, 9.8 meters per second squared will be gravity. When I do this math, that tells me how many newtons this is. Is that math right? Yeah, it probably is. Because it's a little less than 10 and a little more than 20. So 200 newtons is the weight of this barbell, or this weight plate. So if you double plate, how many newtons are you lifting? Double plate is the bar and 2 plates, right?
How much is the bar was?
45, right?
Doesn't matter, I can't do it.
Essentially, you have 5 weight plates, don't you?
Yeah.
So if I have 5 of these, what's my total weight going to be?
Yeah.
1,000 newtons.
Oh, okay. I was going to say it's not 1,000. In pounds, how much is it? 225, isn't it?
Yeah.
Pounds. That's how we do it. That's how we think. But in science, I'm not going to do this. I want to say this barbell or this plate is 200 newtons. I don't measure weight in pounds. I do newtons. I can do 200 newtons times 5. So if you want to mess with your buddies and say, yeah, man, I benched 1,000 this morning. Just leave it at that. Guarantee you they'll be shocked. Because in our culture, it's assumed that when you lift weight, you use pounds. Well, then you can clarify, like, no, I definitely lifted 1,000. Like, here, let me show you. Throw that on the bench. Do 1 rep. Like, see, I told you.
And they're just gonna think you're just like stupid.
No, you're not stupid. They're dumb.
Yeah.
Now, to be fair, you didn't specify your units, so most of the blame's on you. But your statement wasn't wrong.
They were assuming.
They were assuming.
Technically, like, yo, I can lift 200.
That's true. That's true. So it's a half truth. Yeah, exactly. That's why I'm going to be picky on units. Like, on tests and stuff, I will be especially picky. If you give me an answer and you don't tell me the units, it's at least half wrong. Because you're right, you could have told me, oh, it equals 500 watermelons, 500 pink giraffes. I have absolutely no idea what you're talking unless you tell me what you're doing. So anyway, yeah, you could say to your friends, like, yeah, I can lift 1,000 newtons if you can double plate, but... So there are, let's see. What this is going to do is we're going to walk through some of the like concepts that we know just because of this one equation. The first one is that the acceleration of some object is inversely proportional to its mass. One, mathematically, that makes sense, right? It's literally an equation. If I increase this number and keep this the same, I'm basically making a bigger denominator. When I do that, my number goes down, doesn't it? 1/10 is bigger than 1/1,000,000. If If I increase my mass, my acceleration goes down. If I somehow have this force and I increase the acceleration, that means I had to have used a smaller mass. These, acceleration and mass, inversely proportional. If one goes up, the other has to go down, assuming you keep force the same. That makes sense intuitively, right? If I can push with 5 newtons on a 1 kilogram object, 5 over 1, 5 meters per second squared. If I push with that same 5 newtons on a 2,000 kilogram car, I'm hardly going to accelerate it at all. Right? The more mass I have, the smaller the acceleration I can create with a force. That should make sense intuitively. The smaller mass that I have, the larger acceleration I can create with that force. The other one, how do acceleration and force relate? What's their relationship? It's right here. This means proportional. You guys seen that? That's Greek letter sigma. Or no, excuse me, alpha. Sorry. That makes sense, doesn't it? If I have a 1 kilogram object, if I apply a lot more force, it accelerates more. If I can get this object with the same mass to accelerate a lot more, it means I have to have applied a lot more mass. Whenever this goes up the same amount because I'm keeping mass the same. Evan?
Okay, so this might be like a weird, random question.
Okay.
What do those symbols have to do with fraternities and stuff?
I don't know the origin story. Like, at the University of Iowa, there was a bunch of fraternities and sororities. Like, there were the tri-delts, delta, delta, delta. This is a delta. We'll use this symbol a lot in physics. This also means change in. Delta means change. There was, I was never in one.
You encountered the Illuminati and you didn't even know it.
Alpha, what? Delta Chi? Phi? I'm rusty on my Greek letters. Phi, delta, chi, K. I think it's a weird K. I don't know what a phi is.
You just look it up.
Anyway.
Sorry.
You're distracting me. I don't know the origin, why fraternities and sororities name themselves after Greek letters. I think it's, there's some reason, but they just choose to call it, instead of the super awesome fraternity, instead of naming it, they just use Greek letters. And that's just some norm that's been established. We'll use quite a few Greek letters in this class. There's a lot of them throughout science. Anyway, this should make sense, right? If I push on an object a lot harder, it's going to accelerate a lot faster, right? How about, in what situation is the acceleration of an object 0? What situation do I have? If I have a 0 acceleration of an object, what has to be true? It's Thor's hammer. Look at our equation.
What?
I can't have 0 mass, right? Then I don't have an object. I have some object. John's got it. If I have some object with a mass, for me to have no acceleration on that object, what has to be true? John said no force. 0 divided by anything equals 0. That's the only situation that this equation works. Even if I put 0 here, I have an undefined equation. I can't divide by 0. The acceleration of an object will only be 0 if the net force on the object is 0. What happens if I have 2 forces right? I push on my marker in both directions. How is it still not moving or accelerating?
Equilibrium.
In the same direction.
In opposite directions. I push this way and this way. Well, wait, I have a force acting on it in two directions. How does this work? What does that sigma mean?
The sum of.
The sum of.
You add them up, it's 0.
To look at the acceleration of an object, I need the net force, the sum of the forces. If I add 5 and negative 5, I get 0. That gives me no acceleration. That's the only situation that you can have an object that has 0 acceleration. The net forces in whatever direction you're looking at the acceleration, they have to equal 0 for you to tell me that there's no acceleration on that object. Here's a very similar question. These are vectors, right? What has to be true about the direction of both of these quantities?
They're the same.
They're the same.
You push on something in this direction, it's going to accelerate in that direction.
Yeah, if I have a net force in the positive x direction, where's my acceleration?
The positive.
Positive x direction. One, that should make sense. If I push on something and I can actually move it, it's going to move in the direction I push it. That should make sense intuitively. Mathematically, it should also make sense. This is a scalar. This has nothing to do with the direction at all. So then I only have the force as a vector and the acceleration as a vector. Well, for this to be an equation, the vectors have to be pointing in the same direction. Otherwise, what you're telling me is if I push this way, my object accelerates that way. Well, one, that makes no physical sense. And two, it's mathematically incorrect. This would then be an inequality. So those are 4 key concepts that I want you to be aware of. Now, you'll use these a lot. If I tell you the object is not accelerating, you can tell me, boom, no force applied, no net force. I know for a fact. Because the only way to get this be 0 is if your force is 0. If I tell you I increase my force, what happens to my acceleration? Boom, it increases. I know for a fact. Because you know, if I keep an object the same and I increase the force, I have to increase the acceleration. Otherwise, you broke physics. And I doubt any of us are going to be able to do that. Right?
You have to do a challenge.
If I do my math and I say a positive 5 Newton force in the x direction, and I do my math and I get a negative whatever, you're like, whoa, wait a minute. How is my acceleration in a different direction than my force applied? Something's up. Oh, shoot. I added a negative sign, or I did my math wrong. So a lot of these you're going to be able to use, or AP is going to ask you really tricky questions. They're going to say, the mass of an object is increased by 1.5 times. How much does your acceleration change? That's where it gets weird. What you do is you put 1.5 m and then solve it out to get f over m like normal and see what fraction is in front of the acceleration. Would your acceleration go up or down if you doubled the mass?
Yeah.
What do we think?
Yeah, because you're applying the same force to it.
Yeah, the only thing I'm telling you is you double the mass, everything is the same. How does the acceleration change? If I increase my mass, does my acceleration increase as well? They're inversely proportional. If I make this number bigger, it's harder for a set force to move a heavier object, so my acceleration goes down. So up here, to practice this really quick. Two kilograms mass, the force causes an acceleration, so F equals ma. Or wait, I want to do it this way. Well, if this is 2 and this is 10, I have the same force. What happens if I use... Oh, shoot, I gave it away. Dang it.
Answer is 5.
Ah. I have the same force. Right? But I now double my mass.
I'm gonna half the other.
Half the other one. So this actually is 5. What if I have my mass?
Oh, yeah.
Don't I double my acceleration? They're inversely proportional. I want to go to this one. If I got a force acting on my motorcycle, rest in peace. Miss it every day. The mass is 100 kilograms, and it causes a 10 meter per second squared acceleration. What happens if I do the same force on a 1,000 kilogram car?
And you multiply 1 by 10, divide the other 1 by 10.
Yeah. Mainly, real quick, is my acceleration going to go up or down?
Down.
Down. Right? The same force on a much more massive object, way lower acceleration. What happens if I use a dump truck? 5,000 kilograms. My acceleration going to go up, down, or stay the same?
Way down.
Way down. That should make sense. I can't push on a semi and get it to accelerate hardly at all. I can move a motorcycle. That's easy. I can get that thing going. All right, I'm going to skip the rest of these. We can come back to them later. The last thing, introduce a system and a gravitational field. This one is a little weird. There's really no good way to introduce these topics. A gravitational field is this imaginary, like force field that exists. Right? So when we have an object, that's experiencing gravity, it's actually experiencing a gravitational field. Well, that's just this imaginary region where any object inside this force field is under the effect of that force. Well, that's gravity. Right? Technically it goes on infinitely. There's this force field, this region where any object in this force field experiences whatever force is being applied. If I have an object here, the force of gravity always acts straight down. That makes sense intuitively, right? The only reason I'm highlighting this is AP makes a big deal about fields. You can think of them as force fields. It's literally an area where at any point in that field, this force acts. Doesn't matter. Now, at any position, the direction of that force in the field always goes to the center of Earth. That's how gravity works. It's sucking, it attracts other objects to its core. So at any point on Earth, gravity, that's why we know if we have some object, gravity always acts straight down. Whenever we have that force field of gravity, The force of gravity acts straight down to the core. That's also why this is true. If we add up all the forces, and the only force acting is gravity, the force of gravity in a force field on our planet is equal to 9.8. Right? If there's no other forces but gravity acting, it produces the same result every time. This reasoning, this understanding, is how we're able to say, like, oh, acceleration of gravity is always 9.8. Right? The other thing that I want to, again, it'll sound petty, but again, AP makes a big deal about it, is a system. When we're talking about objects, we want to look at the system of objects. I could tell you that there's a wagon, with like some basketballs in them. If I tell you the force acting on the system in this direction, say is 10 newtons. If I say on the system, what am I referring to? Am I referring to this basketball? Am I referring to this wheel? What am I referring to when I say on the system? What's your gut tell you? The whole thing, right? The system. The system is essentially either a collection of objects you consider together. It could be objects you merge into one. They move together. Or you could say you have multiple objects in your system. Right? If I have these forces that are applied, this is my system. This is what I'm looking at. But I have multiple objects in my system, right? The way the problem is worded or drawn will change, like find the overall force on the system. Well, I would add up these forces, right? It could ask me, what's the overall force on the top block in the system? I'm just going to look here. I don't care about anything else. So the system and the object can change. Don't worry too much. We'll do a lot of problems where you'll have to define them differently, or the question will ask about the system, about an object in the system. The system can either be one object, it can be a grouping of objects, or it can be multiple different objects that you're considering. All right? Any questions about system or fields? They're really weird topics, but again, AP makes a big deal out of them, so I have to at least mention them. Any other questions? Okay, so the last thing, I have a couple homework problems that I want you guys to do. So there's only 5 of them. This is to practice Newton's second law that we just did. F equals ma. These problems, there's 5 of them. They're in the book, 4.3. Wow, this is virtual. Again, you guys in class, I'm going to post assignments to Classroom. Hardly any of them you will actually submit, just so that you're clear. Google Classroom will ask you to submit it, but it's just because it's an assignment. You guys turn that into me. I only post them so that you guys are like, oh crap, what problems did Mr. H tell us to do? I have no idea. Go to Classroom, they're going to be there. Because I have to post them for the virtual students as well, so it makes sense to just add you guys. That way it's always there referenced in case you forget.
Well, this way we can assign something like on Friday and then like Sunday night read a message.
Yes.
Oh yeah, that assignment you guys didn't do, it's due tomorrow.
Yes, that is. Also, I was being helpful offering that reminder.
Yeah.
You can't rely on that, all right? I can't remind you all the time, hey, you got a homework assignment due tomorrow.
No, like Google Classroom automatically reminds us.
Oh, it does?
Yeah, the night before.
Okay.
It'll say blah blah due Monday the 14th or whatever.
That's great to know.
That's what I was talking about.
Okay, I understand what you're saying. That is helpful to know. I'm glad it does that. Because I can't remind students all the time. That'd be half my job. But my point is, you guys will be assigned stuff in Classroom. You don't submit it. The virtual students, they have to submit through Classroom. So I just want to clarify, you guys, that's the assignment, but you turned it in paper or in person. Unless I tell you, like, hey, do this lab and submit your results, the screenshots, whatever. All I want you to do, I would recommend reading homework or 4.3, just again to review, get another perspective if you want. Otherwise, there's 5 problems. You don't have, it's not up there. It's just 5 problems that I want you to do to practice Newton's second law. All right? So just so you're clear. So this is what I want you guys to do and bring back for next class. Again, to keep practicing, to try and set up a good system where we introduce and talk about some new topics, do some examples, and then I want to give you guys time to put those into practice, all right? How do we feel about today? Good? Is it tracking so far? Am I going too fast? Is this like way confusing or is it pretty straightforward? Give me some feedback. How are we feeling? I got a so-so. Good. So-so. Medium. Okay. Hopefully these problems will help. One, reading, because they have practice problems or examples in the book. It's like, hey, this guy has a mass of 5 kilograms. Someone kicks him horizontally with 2,000 newtons. How fast does he accelerate? They have some practice problems to show you step by step.
I still think we should just get a ballistic gel and hit something good.
Well, if you can get the ballistic gel, maybe we can get that set up. I don't have the money for that.
Those things are expensive.
Yeah, ballistic gel is very expensive.
Well, I looked at like a full body dummy made of this stuff. It's like $2,000.
Yeah, it's. I think we looked up that it's just a very specific amount of gelatin. That's all it really is. It's basically a specific type of Jell-O, but it's so specific because it needs to imitate the human body, and it's hard to replicate that. That's why it's expensive. Because I think Ethan had found it was like literally just Jell-O. It was just gelatin, but to a very, very, very precise degree so that it simulates the human body, and that's why it's so expensive. Which is ironic.
If we make like a certain type of Jell-O, not near as good as that. We make a certain type of Jell-O, and then we can bash it.
Probably cherry.
Yeah.
You can tell me what data you would collect, what calculations you would run, and what concepts you'd learn. I'd entertain that.
College board and say, can I be exempt from the AD?
Do an entire class, all 10-unit topics on a Jell-O lab.
Yeah.
That'd be mightily impressive if you could get them to.
Like, no, we'd rather you get a 3.
So just, again, virtual students, a reminder, your homework you will submit through Classroom. In person, you guys are just going to bring it back next class. But virtual students, just do the work on a piece of paper like normal, and then just take a picture and upload that. That way I can at least see it.